A logistic function is an exponential function, but it has a limiting value. Usually exponential functions are rapid increase or rapid decrease, if it's growth or decay, but sometimes there is a situation where there's a rapid increase and then it levels off to a certain maximum. For example, if flu is going around campus, people catch it like crazy. Everybody's got the flu, but there's an upper bound because there may be 25,000 students that can catch it. So that it is exponential, but it does have a limiting value. So let's look at what the function looks like. We have usually n of t, standing for a number of something, over a time period, equals m over 1 plus a e to the negative kt power. So m would be the limiting value, that would be the upper bound. A and k are both constants, so we have three numbers to work with. Now there is an alternate version of this where we have n of t is equal to m over 1 plus a times c to the t power. And in this case, m and a and c are all numbers. The c is raised to the t power, but a is not. A is multiplied after you raise c to the t power. And either of these is perfectly useful in most instances. Now let's look at a graph and see what the function looks like with its limiting value. Okay. So let's look at a function f of x equal to 8 over 1 plus 3 times 0.95 to the t. And we want to see what the graph is going to look like. So let's pick some numbers, and we'll just use positive values for t. If I plug in t equal to 0, I look for f of 0. I'll have 8 over 1 plus 3 times 0.95 to the 0 power. Anything to the 0 is 1. So I now have 1 plus 3 in the denominator. 8 over 4 is equal to 2. So our graph starts about 2 when x is equal to 0. Oh, I put an x here and I put a t there. Let me change this to an x so that we match. As we move along, let's jump over to, before we jump, notice that 8 is the numerator and that's supposed to be our maximum. So up here, 2, 4, 6, 8. These are the numbers for y equals 8 that we should approach. I know f of 0 is 2. Let's move over and try f of 25. We'll move over pretty quickly here. If I plug in 25 here, I've got 0.95 raised to the 25th power. Now, 0.95 is less than 1. So if you take 0.95 and put it into a calculator to the 25th power, you're going to have 0.0 with a lot of decimals before you get to a number, because exponential functions either increase or decrease rapidly. So this 0.95 to the 25 is basically equal to 0. So I have 8 over 1. Now we know that at 25 we're not there yet. So we can plug some numbers in and get a number that's less than 0. And it turns out that it's something like, I think it's about 4.3, if I'm thinking right. I think that's about what that one's equal to. If I move up to 50, we get even closer. 1 plus 3 times 0.95 to the 50. Whatever decimal goes here ends up with about 6.5. 25 was about 4.3 to 4.3. 50, about 6.5. And as you increase, You go 100, 150, your values will increase like this and level off. And there is a bit of a dip in here, not a dip, a curve that makes this sort of resemble an S shape. So the logistic function is often called an S curve. Okay. If you pick, say, f of 100, you'll get a lot of numbers that are very, very close to 8. By the time I got to 50, it was already at 6.5. Now let's look at an example that's an application problem to see how this is actually used. So we have our example problem about a fitness club and its membership. The facilities mean they can have up to 500 members. When it first opens for business, which would be time t equal to 0, we have 20 people who come in. After 4 months, it's up to 339. So we want to develop a formula to see over different time periods how close they're getting to 500 members, and to find out over a long time if our function will be accurate and give us up to 500 members, or if it's going to go beyond that. Now, a lot of times people write notation like this, but very often in this course we work with a data table. So let's transfer these numbers into a data table where t is in months, and I have 0, and my number of members in is 20. At 4 months, the number of members is 339. And I want to know how many will there be in the long run. That's another way to phrase it. A long time from now, we refer to it as in the long run. I think for this formula, I'll use the one that has c to the t in it. So n of t is equal to m over 1 plus a times c to the t power. And when you're working with a data table, you're always going to want to use the first point first. So I want t to equal 0, and then my n value will be 20. So I have 20 equals m. M is the maximum, the limiting value. That's our 500 members. Over 1 plus, I don't know a, I don't know c, I know that t is equal to 0. So we start where the input is. C to the 0, anything to the 0 is 1. So my denominator is now 1 plus a, and I'll multiply across times 20. Now, generally, when I've got this, what I do is divide by 20 instead of multiplying through. So if I divide both sides by 20, over here I have 1 plus a, and over here when I divide by 20, I get 25. So when I solve for a is equal to 24. It's a constant. I have found the value, so that goes in here in place of a. So my formula now is n equal to 500 over 1 plus 24 times c to the t. Those values are constant. I move to my next data point to see what information that gives me. N is 339 equal to 500 over 1 plus 24 times c to the 4th power. So, again, I'm going to multiply across by the denominator. So I have 339 times 1 plus 24c to the 4th is equal to 500. And again, I'll divide by 339. So 1 plus 24c to the 4th, 500 divided by 39 is something like 1.47493, something like that. And now I want to solve for c. So I subtract 1, I divide by 24, I get c to the 4th about, let's see now. I'm not sure where my 0 is, so I'm not going to tell you what c to the 4th is. It seems to me that there's either a 0.01 or a 1 point something. But if I take the 4th root of that, then I end up with c equal to 0.375. And this has been rounded because you can see I chopped this off to some decimal places and I had to round. But this does round and always go 4 to 6 decimal places to be sure. So I have a value for c now. So let's go back over to our formula that we have. And I put in all the numbers that I know. I have n equal to 500 over 1 plus 24 times 0.375 to the t power. Now I want to say, well, what happens in the long run? What can I do as far as putting in very large numbers? Well, let's think about this again. 0.375. 0.333 is about a third. So think about what happens if you take 1/3 and raise it to the 10th power. To have 1/3 times a third would be 1/9, times another third would be a 27th, times another third would be 1/81. The numbers are getting smaller and smaller and smaller and smaller. So this piece would be approaching 0, which means I multiply 24 times 0. So all I'm left with on the bottom is a 1. So in the long run, I do have that n is approaching 500. So that is our limiting value. It's the upper bound of this function. And the membership won't go above that. As we look at Newton's Law of Cooling, most people think of it as a cooling down process. There's a cup of coffee that, as you leave it sit on a table, it cools to room temperature. A cake coming out of the oven, sitting on the counter, goes to room temperature. And so it's a cooling process. In business, we can think of it as the sales at the end of a promotion, they return to the usual sales level. After the promotion ends, they go back to their usual level of sales. For heating up, especially in business, it's important because you start an ad campaign and you hope that sales heat up, that the product gets hotter in the public's mind. Or if a new CD comes out and people want to buy it, there's a heating up process as the download of tunes or something continues. Both of these are the same formula. We call it Newton's Law of Cooling. N of T, the number or the temperature after time t, is equal to A plus B times the E raised to the kt power. Now the A, the B, and the K are constants. They're not always shown immediately. Sometimes you have to find them giving information from the problem. The N is the resulting value. After a certain time, you put in some of your other numbers and you end up with a value you're interested in. A is our room temperature, our return to the usual sales level. So A is our usual value, whatever is typical for what the problem. B is the value that you find, and K is the value that you find. But typically you will be given a value for A in the problem. Now, let's look at an example of this. We're going to look at this problem about the test market for an ad campaign. And the test market has 125,000 possible viewers. In the beginning, no one had heard of the product. So at t equal to 0, the number of viewers was 0 who had heard of the product. After 10 days, we were told that 40% of the possible viewers were aware of the product. 40% of the possible viewers. Well, I left a space in my data table over here because I have to figure out what that is. So 40% is 0.4 multiplied times 125,000 viewers. And when you multiply that out, you get 50,000. So under day 10, the viewers who had heard of the product was 50,000. Now we want to figure out how many 90% of the viewers are, because the question asked when, which is at what time, will 90% of the viewers have seen the product. So we take 90% of 125,000. You multiply that out, you get 112,500. And then that is the time that we're looking for. Which day does that happen? So let's see if we can work that out. The example requires Newton's Law of Cooling. N of T is equal to A plus B e to the KT. And sometimes you will see different letters. You will see different A's and B's and C's. But the form is the important part. And as usual, we start with the first point to see what that gives us as far as information. The number of people was 0 at time t equal to 0. K times 0 is 0. E to the 0, e to the 0 is 1. B times 1 is B, but I didn't put in my A. So this tells me that A plus B is equal to 0. A is many things in this formula. It can be called the ambient temperature, if it is a cake problem or a coffee cup problem like you usually see. In some types of advertising, it would be the usual sales. In this, we have 125,000 possible viewers, so that is our pool, and that's the usual amount. And so A is 125,000. So we have 0 equal to 125,000 plus B, which makes B equal to a negative 125,000. So in the formula, I know A is the usual amount, and B is the negative of it. So let's fill those numbers in. N of T is equal to 125,000 minus 125,000 times e to the negative KT. I've used up my first point. I found B. Let's move to the second point. At day 10, N is 50,000. So my number, 50,000, is equal to 125,000 minus 125,000 times e to the negative K times 10. Now, why did I put negative K? K. K is my unknown, so what I need to do now is move things away from K. So I'll start out here at 125,000 and subtract. That will give me a negative 75,000 equal to a negative 125,000 e to the K times 10. To get this negative 125,000 onto the other side, I'll divide negative 75,000 over negative 125,000 equals e to the K times 10. And if you do this division, you get 0.6 e to the K times 10. Now, we've seen before that to get the K, you have to take the natural log of both sides. So I'll take the natural log of 0.6. That takes care of the natural log over here, and the e is gone. I have K times 10, and so then I divide by 10. So I'll get my value for K. K is about negative 0.0511. So I use this K now that I go back up to my formula. I know A, I know B, and I know K. T I don't know, and N I don't know, and that will tell me what I'm going to solve next. Let's put K in here. N of T is equal to 125,000 minus 125,000 e to the negative 0.0511 t. And my question said, when will there be 112,500 people? So I know N, 112,500. What I don't know now is T. So I'll solve for T in the same way that I just got through solving for K. So we have to usually go through this process twice in Newton's Law of Cooling problem. I subtract 112,500 minus 125,000. It's me. I think I subtracted that wrong. Is there one more? I've got to subtract. Let's see. 112, 125, 0, 0, 0, 500, 2, 1. I was right. That took care of that one. Now, this equals negative 125,000. Got enough zeros. E to the negative 0.0511 t. And when I divide this, negative 12.5 over 125,000. I go through the same thing, get my decimal. This gives me 0.1 equals e to the, ln of e to the negative 0.0511 t, so that t is the ln of 0.1 divided by negative 0.0511. And that turns out to be about 45. I always think it's odd when I have strange numbers and they come out to be a nice, neat one. So t is about 45. So that tells me in 45 days, about a month and a half, I'll end up with 90% of all the viewers will have seen the ad campaign.